Hello and welcome to this explainer. Listen, I am absolutely thrilled you're here today because we are looking at something truly fascinating. Just think about a robot for a second. If you strip away its sensors, a robot is really just a blind, deaf block of metal and wire. It has no idea where it is, what it's doing, or what's happening around it. Well, today we're going to change that. We are going to explore the anatomy of a machine and uncover exactly how engineers give robots their senses. Let's dive right in. We have a lot of great ground to cover. We're starting with number 1, giving robots their senses. 2, sight, sound, and proximity. 3, the sense of touch. 4, movement and navigation. And 5, the purpose of perception.
Section 1. Giving robots their senses, perceiving the world.
So a computer's code lives in this perfectly logical mathematical box, right? But the real world is messy and chaotic. Sensors act as that crucial bridge between the two. They allow the machine to actually perceive and interact with its environment. And what's truly mind-blowing is how closely we can map these dense technical components directly to our own human biology. Where we have eyes to see, robots use cameras and LiDAR. Where we have ears, they use microphones. Our skin maps directly to tactile and temperature sensors. Even our inner ear, the thing that gives us our sense of balance, has a direct robotic equivalent in gyroscopes and accelerometers. The engineering is basically mimicking biology.
Section 2, sight, sound, and proximity. Perceiving at a distance. Think about a standard camera sensor. This acts as the robot's eyes. It captures visual information, images, and videos that the robot system processes to extract data about its surroundings. I mean, this is exactly how self-driving cars manage object recognition, obstacle avoidance, and even detect highly specific things like a stop sign. It's taking in the chaotic visual world and turning it into actionable data. But robots aren't just limited to standard video. They have superhuman senses too. This brings us to LiDAR, which stands for light detection and ranging. Instead of just passively taking a picture, a LiDAR sensor actively shoots out lasers to measure the exact distance to objects. This gives autonomous vehicles laser-guided spatial awareness, allowing them to literally map their entire environment in incredible 3D detail. And it's fascinating to look at the different ways machines can see distance. We just talked about LiDAR using light, but we also have ultrasonic sensors. Instead of lasers, an ultrasonic sensor works exactly like a bat's echolocation. It emits high-frequency sounds, frequencies that are entirely invisible and inaudible to us humans, and then it just waits for the sound waves to bounce back. It's an incredibly effective way for robots to figure out the proximity of objects and just avoid bumping into things. Distance isn't just about objects, though, is it? It's also about communication. A simple microphone sensor serves as the robot's ears, converting physical sound waves in the air into electrical signals. This is absolutely foundational for human-machine interaction. It acts as a speech recognition sensor, so a robotic system can understand and process our spoken commands. Okay, so we've given our machine the ability to see lasers, hear high frequencies, and process spoken words. Our robot can see and hear from a distance perfectly well. But here's the question. How does it safely interact with the physical objects right in front of it? How does it actually touch the world? Section 3, the sense of touch, feeling the world. Just seeing an object isn't enough if you need to pick it up without crushing it. We need to explore how robots replicate the human sense of feeling and pressure. Let's compare two really cool components that solve this. First is a basic touch sensor. It mimics the simplest sense of touch to detect physical contact. Think of pressing your fingerprint on a screen, or a robot gently bumping into an obstacle just to know it's there. But then we have the force sensor. This is much more advanced. It doesn't just know if it's touching something, it measures the exact amount of force being applied. This is what allows a robotic hand to grasp a fragile object firmly without breaking it, or to monitor fluid pressure in a heavy industrial setting. Touch also involves feeling hot and cold, right? In robotics, we use temperature sensors, specifically things called thermistors and RTDs. Now, I know those terms sound a bit intimidating, but the concept is actually brilliantly simple. They monitor heat by changing their electrical resistance as the temperature changes. So they basically act as the robot's skin, detecting environmental changes and preventing internal components from dangerous overheating. In reality, these take a few different forms. You have these tiny, flat, coin-like chips called thermistors. You'll find those in thermostats and medical devices. And then you have RTDs, or resistance temperature detectors. They look much more heavy-duty, mainly because they are. RTDs are made of high-purity materials to provide a highly accurate linear response to temperature. That's exactly why you'll see them constantly used in intense, large-scale industrial controls. We are making great progress here. We've given our robot eyes to see, ears to hear, and skin to feel pressure and temperature. But wait, imagine standing up right now and closing your eyes. You still know which way is up, right? You can still keep your balance. How does a machine do that? How does it know its own orientation in space?
Section 4, Movement and Navigation, Inner Ear and Direction.
To give a machine its inner ear and its innate sense of direction, we rely on two unsung heroes of motion. First, the accelerometer. Just like the name implies, it measures the acceleration and speed changes of an object. It's what makes your pedometer or motion tracking system work. And second, the gyroscope. A gyroscope measures the rotation and angular velocity of an object. If you want your robot to balance, or if you want an image stabilized in a virtual reality headset, you absolutely need a gyroscope.
Now, once the robot can balance, it needs to know where it's going. We have the GPS sensor, which uses satellite signals to locate the robot globally for navigation and tracking assets. And then we have the magnetometer. This is literally just a digital compass. It measures the Earth's magnetic field to help with navigation and even metal detection. Together, these basically guarantee the robot never gets lost.
Section 5. The purpose of perception. Synthesizing data. So we've looked at all these incredible individual components, but how do they form a complete nervous system that actually drives automated behavior? Engineers structure this chaos neatly into two main categories. First is the sensor measuring the internal state of the robot, like a gyroscope checking balance, or the external environment, like a camera looking at a traffic sign. Second, does the sensor require physical contact, like a force sensor gripping a cup, or is it non-contact, like LiDAR shooting a laser across a room? This simple framework takes the sheer messiness of the physical world and organizes it into a structured, manageable system. Which brings us to the crucial point. What is the ultimate function of all these sensors? It boils down to 4 simple steps. 1, they measure physical quantities, temperature, velocity, pressure. 2, they detect changes in the environment, like an obstacle suddenly appearing in the light. 3, they take that data and provide feedback to the robot's control system. And 4, that feedback loop enables real-world automation in manufacturing, transportation, and robotics. Data goes in, the computer processes it, and boom, a physical automated action comes out. This quote from our source material perfectly captures the core takeaway today. Sensors play a crucial role in enabling robots to perceive, interpret, and respond to their surroundings. Without them, there is no interpretation. There is no response. Sensors are, without a doubt, the fundamental building blocks of robotic independence. I want to leave you with one final thought to chew on. Today, we saw how we're building robotic sensors to mimic human biology. But we also saw that LiDAR uses lasers, ultrasonic sensors hear frequencies we can't hear, and infrared sensors see light we can't see. As these robotic sensors continue to develop far beyond our own biological limits, we really have to ask ourselves, whose view of the world is actually more complete, ours or the machine's?